In this lecture, we will discuss principal component analysis as a dimension reduction method. In machine learning, we frequently deal with high-dimensional data. High-dimensional means we have many attributes in the dataset. If you keep your data as a matrix where each row is a sample and each column is a different attribute, high-dimensional means we have too many columns. Too many is kind of relative and depends on what you want to do with your data. When the data is low-dimensional, say you only have two features, width and height, it is easy to visualize it. You can create a 2D plot and show each sample as a point in two-dimensional space. If, say, you are using Bayesian decision theory, you only need a probability distribution function of two variables, which is mathematically and computationally manageable. But what if you had 10 or 100 or 1000 dimensions? With such high-dimensional data, visualization is not directly possible. We can't really show a 100-dimensional point in 2D. If we arbitrarily choose to show only two of the attributes, we would be ignoring the information contained in the remaining 98 dimensions. With high-dimensional data, classification also becomes problematic. We talked about curse of dimensionality, where one would need an exponential number of samples as the dimensionality increases. So it is desirable to take a high-dimensional dataset and transform it to a few dimensions. The question is, can we do that without losing much of the information contained in the data? Before I describe principal component analysis as a technique for dimension reduction, I'll give a quick review of what covariance means and remind you of some of the matrix operations in linear algebra. If you are not comfortable with the linear algebra given here, I would recommend that you consult a more detailed resource on linear algebra. You are all familiar with the variance of a single variable, which describes the spread of that variable around its mean. Covariance of two variables describes how they change or move together. It is calculated as the expected value of the product of the differences of the variables from their means. Here, Ex is the expected value, also known as the mean or average value of x. The expected value can be calculated as the probability-weighted sum of these values. Each term in the covariance matrix is calculated using this formula as the covariance of the two variables represented on that row and column. The diagonals are the self-covariance, in other words, the variance of each variable. By this formula, you can see that the diagonal will always be positive, because we would be taking the square of the same value. But the off-diagonals can be positive or negative. From the same formula, we can infer that the covariance matrix is a symmetric matrix because the covariance of B with A is same as covariance of A with B. If the covariance of two variables is positive, that means they tend to change in the same direction. When one is above its mean, the other one is also above its mean. If the covariance of two variables is negative, that would mean that they tend to change in the opposite directions. When one is above its mean, the other one tends to be below its mean. These properties should sound familiar to you. The correlation coefficient has these properties too. Correlation is essentially a normalized version of covariance. We divide the covariance with the standard deviation of each of the variables, which gives us a number between -1 and 1. Remember that the standard deviation of a variable is the expected value of its difference from its mean. The standard deviation of x can be written as the expected value of x minus mean of x. The covariance value is sensitive to the scale of the numbers we are working with. Just by looking at the magnitude of the covariance, you cannot really tell whether the two variables are correlated. Here we are showing a two-dimensional data set, and each point here is a sample, and x and y coordinates represent two attributes. The covariance of x and y is 7.6. But just by looking at the number 7.6, we cannot really tell whether the two variables are correlated. The fact that these points are lined up along a line tells us that the correlation should be close to 1. And here the covariance is minus 3.8, and the correlation is around minus 1. Here are additional examples showing correlation of two variables. Essentially, when the points lie on a diagonal, they are highly correlated or highly anti-correlated. When correlation is 0, on the average, you cannot really tell whether one of the variables is going to have a high or low value if you knew the value of the other one. I would like to point out that the correlation is a linear relationship. Sometimes there may be a strong pattern or relationship between the two variables, such as in this circle example. But this pattern cannot be captured as a linear relationship. You have to keep this in mind when we discuss principal component analysis. When we reduce the data using PCA, any nonlinear relationships between the variables can get lost during the transformation. Let's now discuss some of the special types of vectors and matrices. A vector is an array of numbers. For example, p equals 4, 3 is a vector in two-dimensional space with x-coordinate 4 and y-coordinate 3. Orthogonal vectors are those when you take the dot product, you get 0. The dot product of two vectors is defined as the sum of the products of their individual components. For example, let's take a vector q at minus 3 and 4. If we take the dot product of p and q, we would get 4, 3 dot minus 3, 4, which is equal to 4 times minus 3, which is minus 12, plus 3 times 4, which is 12, giving us 0. Therefore, p and q are orthogonal vectors. A common way to show vectors graphically is to draw an arrow starting from the center of the coordinate system to the point. So that's my vector p, and this is my vector q. Geometrically, orthogonal vectors are perpendicular to each other. If you have a set of vectors denoted as p1, p2 all the way to pk, they can be linearly dependent or linearly independent. They are linearly dependent if you can find constants a1, a2 all the way to ak such that when you multiply them with the vectors and add them up, you would end up with the vector 0. If a set of vectors are linearly dependent, that means you can pull out any one of them and write it in terms of the other vectors. Let's give an example. Let's use three vectors, p at 4, 3, q at 5, 2, and r at 6, 7, and see if these vectors are linearly dependent. If we can find constants to multiply them and we get a 0 vector from their summation, then they must be linearly dependent. Let's find some such example constants. I'm going to multiply p with a, q with b, and r with c. And I get 4a, 3a plus 5b, 2b plus 6c, 7c. And I'm going to set this to be equal to the 0 vector. In two dimensions, the 0 vector would be just two zeros. And we can write this as two different equations. 4a plus 5b plus 6c should be equal to 0. And similarly, 3a plus 2b plus 7c should be equal to 0 as well. There are more than one set of constants a, b, c that will make these two equations 0. We just need to find one set of example values. I'm going to arbitrarily pick c equals minus 7. It doesn't really matter what you pick so long as it's not 0. The goal is to find some example values of a and b. After I plug minus 7 into the equations, I get 4a plus 5b is equal to 42, and 3a plus 2b is equal to 49. When you solve these two equations, you will find that a is equal to 23 and b is equal to minus 10. Since we have found some example ABC values that when we multiply with our vectors, their summation ends up being the zero vector, we would claim that these PQR vectors are linearly dependent. Linearly independent vectors are when you cannot find any such constants, a1 through ak, that can possibly make the summation zero, except of course when each of the a's are exactly zeros. Let's give an example of linearly independent vectors. The orthogonals that we described before should be linearly independent. We'll take p equals 4, 3 and q equals minus 3, 4. And we'll multiply p with a and q with b. We get 4a, 3a plus minus 3b, 4b equals the zero vector. And we can write this as two different equations. 4a minus 3b equals 0. 3a plus 4b equals 0. When we solve these two equations, the only way that these two equations are satisfied is when a is equal to 0 and b is. We cannot possibly find a non-zero set of a and b values that would make this summation 0. Therefore, p and q are linearly independent vectors. Let's get into slightly more complicated concepts. The eigenvectors of a matrix capture its essence. They sort of provide a concise summary of the matrix. An eigenvector x is defined as a vector that when we multiply the matrix with that vector, we get the same value as multiplying a constant non-zero number with x. This special constant gamma is called the eigenvalue of the matrix with respect to x. A matrix can have more than one eigenvector, each with its own eigenvalue. The eigenvectors corresponding to distinct eigenvalues are linearly independent. The process of finding all of the eigenvalues of a matrix is called eigenvalue decomposition. In other words, we take a matrix and we break it down to its eigenvalue and eigenvectors parts. Eigenvectors and eigenvalues are used in solving a number of linear algebra problems. We'll see how they are used in principal component analysis. They are also used to efficiently calculate the power of a matrix, to find solutions of a system of differential equations, and in population growth models. With matrices, we don't really do division. Rather than saying that we divide a matrix S with a matrix T, we instead say that we multiply the matrix S with the inverse of the matrix T. The inverse of a matrix is defined through multiplication, just like we would define the inverse of a scalar by multiplication. The inverse of the number 5 is 1 over 5, because when we multiply them together we get 1. In matrices, the identity matrix is sort of the equivalent of the number 1 in arithmetic. An identity matrix is a matrix whose main diagonals have 1s and all off-diagonal values are zeros. The inverse of a matrix is defined as a matrix that when we multiply with A, we get the identity matrix. For example, the inverse of this matrix is this one right here, and we can confirm by checking that the multiplication results in identity matrix. So let's do that. This is matrix A, and we're going to multiply it with the matrix inverse of A. To multiply these two matrices, we take the first row of A and the first column of the other matrix and multiply those together, and we get minus 3.5 plus 4.5, which gives us 1. To get the next element, we're going to take the first row again and now multiply it with the second column of the other matrix, and we get 0.5 minus 0.5, which gives us 0. The next element is calculated by taking the second row of the first matrix multiplied with the first column of the second matrix. 9 times minus 3.5 is minus 31.5, and 7 times 4.5 is plus 31.5, giving us a total of 0. And the last element of the resulting matrix can be found by taking 9 and 7, multiplying it with 0.5 and minus 0.5. 9 times 0.5 gives us 4.5. 7 times minus 0.5 gives us minus 3.5. And when we add these together, we get 1. And we have confirmed that the multiplication of these two matrices gives us a 2 by 2 identity matrix. Not all matrices have an inverse. For example, when one row or column of a matrix can be written as a linear combination of others, in other words, when the rows or columns are linearly dependent, that matrix would not have an inverse. There is another type of matrix called pseudo-inverse. It is kind of a fake inverse. When you multiply a matrix with its pseudo-inverse, you don't really get the identity matrix. But the result that you do get, when you multiply it with A, you get A back. So A times pseudo-inverse of A kind of acts like an identity matrix, even though it is not. Another feature of pseudo-inverse is that when you multiply A with pseudo-inverse of A, you get the same result as the transpose of that, which is another way of saying that this resulting matrix is really a symmetric matrix. Here I am showing an example of a pseudo-inverse. Let's look at this matrix A. The second row of this matrix is just a constant factor of its first row. Because this matrix has rows which are linearly dependent, we can write one in terms of another one. Its inverse does not exist. But its pseudo-inverse is given down here below. When we multiply A with its pseudo-inverse, we get a resulting matrix that is not really an identity matrix, but it will act like an identity matrix. So let me call this one a fake identity matrix. When we take this fake identity matrix and multiply it back with A, it has no effect in the multiplication. It will give us A back. So it is as if we multiplied 1 with A, or the identity matrix with A. This fake identity matrix only has this property when you multiply it with the matrix that was used to generate it. If you were to multiply this fake identity matrix with a different matrix, you are not really guaranteed to get B back. Basis vectors are vectors that you can use to represent all the other vectors in the same space as linear combinations of. We previously looked at the two vectors P and Q that were orthonormal to each other. But these vectors are not really basis vectors because their lengths are not ones. In fact, they have a length of 5. If we made each of these vectors unit length, then they would be basis vectors. So let's change P to be at 4 over 5, 3 over 5. And let's make Q to be at minus 3 over 5 and 4 over 5. So that's my new P and my new Q. These new P and Q vectors are both orthonormal and they have a unit length of 1. Let's take another vector at, say, 20 and 100. And let's call this vector R. You can show that R can be written as 76 times P plus 68 times Q. If you imagine that we placed a ruler or a measuring tape, one along the direction of P and the other one along the direction of Q, this new vector R would have a value of 76 on the first ruler and a value of 68 on the second ruler. Vector r can be written as 76, 68 in this P and Q coordinate system. In summary, what we did was we took a vector r which had coordinates of 20 by 100 and we rewrote it in a different coordinate system as 76 and 68. You have to keep this process in mind when we are discussing principal component analysis because we're going to do something very similar. We're going to take the data values in our original space and transform them into new values in a different coordinate system. A final type of matrix I'd like to introduce is an orthogonal matrix. An orthogonal matrix is a square matrix whose rows and columns are orthonormal. If a matrix E is an orthogonal matrix, it would have the following properties. The transpose of an orthogonal matrix is equal to its inverse. Consequently, when you multiply an orthogonal matrix with its transpose, you would essentially be multiplying it with its inverse, and you would get the identity matrix as a result.